Hello, everyone. My name is Enoch Oseibonsu, and welcome to my final project presentation for DSA 5303. Today, I'll share my work on comparing classic financial models with modern machine learning methods for option pricing. Specifically, I'll cover the Black-Scholes model. I'm going to dive into linear regression, random forests, XGBoost, and neural networks. On the agenda today, the structure of the talk is going to be basically, I'm going to give you an introduction, why option pricing matters, and then we're going to do a quick overview of the data that was used for this project, and then the methodology, which models were chosen and why they were chosen, the implementation process, how models were built and evaluated, results and evaluation, what performance we observed, and then conclusion and key insights. Options grant asymmetric payoffs, enabling hedging and speculation. Pricing is crucial to avoid arbitrage and mispricing in financial markets. The Black-Scholes model, introduced in 1973, revolutionized pricing theory but assumes constant volatility and frictionless markets, which often doesn't hold in reality. This study investigates whether machine learning can improve accuracy using real-world market data. So, a quick data overview. Our data set includes call and put options on SPY, AAPL, and MSFT. I pulled data via Y-Finance in Python, the Python library, focusing on 5 upcoming expiration tickers across April to June of 2025. I collected strike price, bid ask, implied volatility, and expiration. After cleaning, I added calculated features. Here's a sample snapshot of the enriched data. So this is the raw data snapshot that was taken from the Python library uh, by the code that was used. And then, so you can see the bid, the ask, the implied volatility, and etc. So this is the raw snapshot of the data. And then some data pre-processing was done. So this step combined calls and puts across tickers. I removed missing data, calculated mid-price, moneyness, underline divided by strike, and time to maturity in years. And then I encoded option types. So call was a 1 and a put was 0. And then implied feature scaling for models like neural networks. These steps ensured clean, consistent input for model training. And as you can see here, we have a clean data sample. Now we're going to start with the Black-Scholes model. I implemented the Black-Scholes formula using inputs, current price, strike, time to expiration, risk-free rate, and implied volatility. While it's fast and interpretable, its assumptions limit its predictive accuracy in real markets. Nevertheless, Black-Scholes serves as a key theoretical benchmark. So these were the inputs, and then the formula that was used for each option, and then after the calculation, I have I printed a snapshot onto the screen of exactly what I had after doing all the calculation. So we're gonna talk about the code. And then basically, here's the implementation snippet. So a function computing option price row by row. After that, I calculated mean absolute error, the root mean squared error, and then the R squared score to quantify its precision on our test sets. Blasco's had an MAE of 32.9423, RMSE of 47.9796, and an R squared of 0.236. This was indicative of weak explanatory power. So after that, I moved on to start working and preparing my data for machine learning. So I trained a linear regression model on features like strike, moneyness, implied volatility, and time to maturity. It captured linear trends and interactions. Performance improved over the Black-Scholes with MA of 28.2930, RMSC of 39.3197, and R squared of 0.3207. From the graph, comparing this graph to the earlier graph of the Black-Scholes, the predicted versus the market prices, you could clearly see that the Black-Scholes actually deviate a lot from the perfect prediction. But when you come back to the linear regression, it provided an improvement. Linear regression actually provided an improvement on the Black-Scholes. So I went ahead and I decided to train other machine learning models, which were nonlinear. So the next model that I trained was random forest, which is a nonlinear model. So then I used a random forest regressor that handles nonlinear relationships. This model further lowered errors. You can see that the MAE here was 1.198, RMSC was 2.4504, R squared was 0.9974. And you can see that, but this shows slightly less explanatory variance. So R squared was 0.9974. So due to its handling of outliers. So here's a scatter. So from the scatter plot, you can see that indicate the implied volatility and moneyness were the most influential predictors. So from the scatter plot, you can see that it actually did a pretty good job. A near perfect prediction. It did a near perfect prediction on our data. So random forest outperformed the linear regression and outperformed Black-Scholes. So I went ahead and then trained another model, the XGBoost. And so then I used XGBoost regressor that handles nonlinear relationships. So XGBoost, a gradient boosted tree model, is a state of art in tabular data modeling. It achieved an MA of 1.9422, an RMSC of 4.2191, and then an R squared of 0.9922. A clear improvement, right? Its boosting mechanism helps generalize better than the random forest, balancing error and variance. The predictive scatter plot confirms its tight alignment with actual prices. So you can see right here that XGBoost also did a pretty good job, ultimately performing better than the Black-Scholes model. The red line of the perfect prediction, you can see how the scatter plot shows how all the data is essentially around the perfect prediction. And then this is on the left, you can see the code, a sample code of how this model was trained on the data that was used. And then I went further and then I trained another machine learning model on this data. So we can have a variety of machine learning models to compare with the Black-Scholes model, which is the traditional a model that very popular that everybody is used to. So my next model that I trained was the neural network. And I also implemented, what I did was I implemented a two-layer feed-forward neural network, right? Scaling inputs beforehand. So after 50 epochs, it reached the lowest MAE, right? MAE of 1.8269, and then the highest R squared of 0.9965. This plot show the scatter plot on the right shows tight clustering from actual versus predicted values. Despite requiring longer tuning and more computation, the neural network achieved excellent accuracy. So from all the models that we've dealt with so far, the neural network was able to achieve excellent accuracy. And as you can see on the scatter plot on the right, the perfect prediction line. And then it has a lot of the points really close to the perfect prediction line. And on the left, you can see the sample code and then the performance plot on the right. So from what we've done so far, you can see that starting from black skulls and coming into machine learning is actually providing a lot of improvement on the things that black skulls was not able to capture. It's providing a lot of improvement on the things that machine learning was not able to capture. Now, so then after implementing and training these models on the data, I began doing a comparison, model comparison. So if you put the all five, if you put all five models side by side, you could see that there's an improvement starting from black skulls all the way to neural networks. You can see that each model improves, especially with the machine learning models, improves on the black skulls model. So clearly from this project, it's becoming obvious that machine learning is able to capture the intricate relationships that's going on with option pricing. And it's better at predicting, it has a better prediction power, I would say. So the bar compares performance metrics side by side. Machine learning models, particularly XGBoost and neural network, dominate across MAE, RMSE, and R squared. The Black Scholes model sits at the bottom, reinforcing the advantage of data-driven methods for real market pricing. Now, so these are some of the challenges that I went through when I was performing this project. So there were a few challenges. The first one is market noise. So real world noise. So price variations due to liquidity or external market shocks complicated predictions. This is something that from my research, this actually complicated a lot of the predictions. And also data quality. So Y Finance provided me the raw data, and then I had to clean it and pre-process and do all the necessary steps needed to actually get the data ready for training on these models. So handling missing values, that's number one, and ensuring balanced volumes, which required filtering. And then also model tuning. So computing time for neural networks, yes. So especially for neural networks, finding the right network depths, learning rates, and epochs took experimentation. So that took a while. I had to do like a few I had to do a few iterations to be able to get it right with that. Key contributions that key contributions to this project and this topic was I was able to implement a fully integrated options data set spanning multiple tickers and expirations. I was able to provide a comparative study across all the 5 models, and then an empirical evidence that machine learning, especially XGBoost and neural networks, improves pricing accuracy over traditional models. So building a complete machine learning pipeline, compare classical and machine learning models, and then improve predictive accuracy. So in conclusion, machine learning models significantly outperform the classical Black-Scholes model in predicting option prices. While theoretical models lay the foundation, data-driven approaches provide a practical advantage. Future work could explore deep learning architectures, market calibration, or real-time prediction with live data feeds. And so I used a few references, and here are some major references that I used. Foundational papers like Black and Scholes 1973, textbooks by Hall in 2018, software libraries such as scikit-learn, Keras, XGBoost, and tools like Y-Finance. These inform both theoretical models and implementation. This brings to an end of my presentation of the project for the course DSA 5303. Thank you.